Oh, this is the last question, question 11. Here we have two different dimensions. First, we observe gender, male and female is one categorization, and we assume that there are only high school graduates and college graduates. So I assume they are also sum to one. So then these already show you the linear dependence relationship among these variables. Okay, we have two relationships. So let me expand here. So then I'm not going to write much about it here. So in the first, excuse me. So I will put it down here, and let's think about it. In the first equation, we have actually 5 regressors, intercept, MFHC. So then both of the linear dependence cause a problem here, so it is not identified. Okay, that is clear. But you have to note that there are two linear dependence problems. You may also define X in this way and show the 5 by 5 matrix is not invertible. This is also a correct way to show that, but I would not try to calculate 5 by 5 matrix. I don't know how to do that, so I'm not going to do that here. And in the second equation, the intercept is dropped. Intercept is dropped, but still it has MFHC, which causes pretty much the same linear dependence like this. So it is still not identified. Okay? And even if you drop the C, like in the third equation, intercept MFH. In this case, we still have M plus F equals to 1. So H is now innocent. H does not cause any problem here because C is dropped. So without C, H is not a problem. However, the other three still cause a problem. So now I wanted to illustrate two linear dependence can happen like this. And in that case, we have to drop two regressors. Dropping one regressor does not help. Okay. And finally, we have only three regressors. They are okay. So let me write a little more about that. So in the end, when you have like something like this, so you dropped female and you dropped college grads, then you get these three, and then also, as I said, you may calculate this to show it's invertible. And also, you may just argue that this is not true with positive probability. That is what you have to show that. Earlier, when I write, like say this, then actually it should mean it happens 100%, but now you need, this is not the case. Okay, for this to be true, but you have to have some problem, like some conditions. You need a condition. For example, the probability of male cannot be 100%, cannot be 0%, right? If everybody is woman or everybody is man, then if everybody is man or everybody is woman, then already like one is like this when everybody is man. And when everybody is woman, variance of mi will be 0. So it will fail multicollinearity. It will fail the full rank assumption again. Same thing. You have to have high school grads less than 100%, but larger than 0%, right? Same idea. If everybody is high school grads, then it's collinear with the intercept. But if everybody is college grads, there is no variation in the variable. So also that is another full rank consumption problem. So you need condition 1 and condition 2. And finally, you need one more condition. That is probability of, like, so what we worry about here is if m equals to h, then we have a problem. For example, men are always high school grads, but female are always college grads. So this is another disaster, right? Basically, in this case, we have one variable, not two, right? So somehow, if all men are high school grads and all women are college grads, then there will be some problem. Okay, so that means we have to assume that probability for man equals to 1, high school equals to 1 should be like this. And also should be like this. Okay, so something like that. You have to have all the each groups. So then you can estimate, you can identify the each groups, right? So if you calculate the 3 by 3 matrix's determinant, then I believe you will get these mathematical conditions, right? So here I'm just saying that in more casual words. Now then, okay, let me simplify this. And the next questions. So now the identification problem is okay, but it is not fully general. So we would like to add another coefficient there. So that is, we consider, plus we are considering here, let's say lambda 0 times, I will consider the interaction h interaction term like this. So this is the fully general model, because as before, we are going to define mu of mc, mu of mh, mu of fc, mu of fh, right? You know what they mean. Men college graduates, men high school graduates, and female college graduate, female high school graduate. So if each group has positive probability, then we can identify their group average, okay? And then you can calculate, like using the equation. From the equation, we can show that it's 0, nothing, and mu mh equals alpha 0 plus m is 1, h is 1, and m times h is 1. Mu fc is alpha plus beta m is 0, h is 0, so everything else is 0. There is nothing more. Mu fh is alpha 0 plus m is 0, h is 1, m times h is 0 too. So we get these, we can represent the group average using the equation like this. Then what you can do here is, now I would like to rewrite, solve for the unknown parameters, alpha, beta, gamma, delta, right? So alpha, these are unknowns, but mu is what we can calculate, what we identify. So alpha is simply the reference group, because F is dropped, C is dropped. So female college graduates are the reference group. So we get alpha capturing that reference group's average. Beta is mu mc minus mu fc, right? So beta is the coefficient in front of man, right? So and so it's a coefficient of man, but the second dimension is fixed at the reference group. Reference group is C, right? But from the reference group, it changes to man. Reference group is FC, but because it is coefficient of m, we change f to m, okay? And it's also different from the reference group. Gamma is mu fh minus mu fc. Same thing, from the reference group, it changes, it updates the education. So we are calculating the difference. And finally, mu mh, so the finally delta, not delta, excuse me, it should be lambda. Lambda is updating both, right, m and h from the reference group. And how do we do that? You may write it as so from the reference group, we update the education, and this is not a reference group, but like from man and college, we are just changing education. So we do dimension by dimension for each information. But at the same time, you may rewrite this as mathematically they are the same thing, okay? So in like 2 by 2 things, like we go to here and then here, or go to here and then here. So it does not matter. So it's, in any case, it is difference in differences. That is the key idea. And we identify everything. And also the simple rough idea is when you have 4 groups, you can handle up to 4 parameters. Right? That is very intuitive. Right? Each parameter takes care of something in the model. So then what additional restriction did we have in an earlier equation? We are in this general model. The reason why we are studying the general model is because we have to understand that if you did not have the interaction term, that means lambda equals to 0. You are imposing this restriction. This assumption was imposed in the previous regression, like this one or whatever. Anyhow, so in the previous regression, we are assuming lambda equals 0. That means the college premium education gap does not change for different genders, or the gender gap does not change is the same for all education groups. So either way, they are anyhow the same difference in differences. We are making that assumptions into our model.